We're now going to discuss stopping times for continuous time filtrations. And we're going to borrow a lot from what we did in lectures 45.1 through 3 on stopping times in discrete time settings. But there are some important subtle differences that we need to focus on here. Given a filtered probability space indexed by the whole positive real line, a stopping time is a random variable on the same probability space, taking values in the positive or infinite reals, which satisfies the property that for all finite positive time t, the event that tau is less than or equal to t is in the filtration at time t. Now notice in the discrete time setting, we wrote two equivalent statements for this. The first was that tau is bigger than t. And that remains true here, since ft is a sigma field, and so is closed under complement. In the discrete time setting, we also had a characterization that this was true if and only if the event that tau is equal to t is contained in ft. And that is no longer true in this setting because, of course, the time interval is not a countable union of the times involved anymore. So we will rarely talk about these events and instead focus on these ones. Let's also note an important distinction between the continuous and discrete time settings. In the discrete time setting, the event that tau was less than t was equal to the event that tau was less than or equal to t minus 1, where the time interval was a set of natural numbers. And therefore, that event was in f t minus 1, which linked with what we called predictability. Well, we are going to have a notion of predictability here too, but this is of course no longer true in the continuous time setting. And in fact, we get different kinds of random times if we work with these events rather than these ones. So we give them a different name. Tau is called an optional time if the event that tau is strictly less than t is in the filtration at time t. For every strictly positive time. Of course, this statement doesn't make sense. If t is equal to 0, we just get the true statement that the empty set is in the sigma field at time 0. Now, these are of course not unrelated kinds of random variables. Stopping times are examples of optional times. Because if tau is a stopping time, then the event that tau is less than t is the union over all natural numbers of the event that tau is less than or equal to t minus 1 over n, basically by the Archimedean property for the real numbers. And since tau is a stopping time, this event is in ft minus 1 over n, which is contained in ft since this is a filtration. And so this union is in ft, which shows that tau is also an optional time. But the converse is generally false. Optional times aren't necessarily stopping times. That, it turns out, however, has more to do with a defect of the filtration than an essential difference between the kinds of times. To understand that statement, we're going to talk about peaking infinitesimally into the future or restricting infinitesimally into the past in our filtration. For any non-negative but finite time t, we define, for our given filtration, a new sigma field ft plus to be the intersection over all times in the strict future of t of the sigma field fs. This is clearly a sigma field that contains ft, but in principle it could be bigger than ft. Similarly, for any strictly positive and potentially infinite time t, we define ft minus to be the sigma field in the instant before time t. In other words, we're going to take the union of all the sigma fields at times less than t. But the union of sigma fields is not necessarily a sigma field, so we better take the sigma field that it generates. Now, ft minus is clearly contained in ft, but again, it could be strictly contained. And just to shore up the notation, we will define f0 minus, which doesn't make sense from this notation, to just be the same as f0. On the other hand, we'll define f infinity plus to be the same thing as f infinity minus from this definition, which is what we have all along been calling F infinity. Now, it's elementary to check that Ft plus as T ranges forms a new filtration. It's a filtration that contains the old one. Similarly, Ft minus is a filtration that is contained in the old one. We say that a filtration is right continuous if Ft plus is equal to Ft. That is, by peeking infinitesimally into the future, you don't get any new information. And we could comparably define left continuity, but we won't have need for that in these lectures. It's important to note that most filtrations in the wild are not right continuous. And this right continuity has nothing to do with continuity or right continuity of the paths of a process. Indeed, it's a nice exercise to show that if you take the natural filtration generated by a Brownian motion, that filtration is not right continuous. It is, however, possible to augment it to make it right continuous. In fact, that's always true. Given any filtration to start, we can find a filtration containing it that is right continuous. Indeed, we can just take Ft plus. This filtration is right continuous. And that's just because if we take Ft plus plus, which is defined to be the intersection over all s greater than t of Fs plus, well, that's the intersection over s greater than t of the intersection over r greater than s of Fr. But this double intersection is nothing other than the intersection of all r bigger than t of Fr, which is the definition of Ft plus, showing that Ft plus is indeed right continuous. We've now struck upon the main reason why we have from the beginning said we might want to consider a larger filtration that our processes are adapted to rather than always working with the natural filtration generated by the process. Those natural filtrations are rarely right continuous, but for many technical reasons that will be clear in the next lectures, it is usually convenient to assume that the filtration is right continuous. And therefore, if we start with the natural filtration, we'll usually want to augment it to make it right continuous, like this. Now, the difference between stopping times and optional times has everything to do with this right continuity. A random time tau is an optional time with respect to the original filtration if and only if it is a genuine stopping time with respect to this augmented filtration. And in particular, that shows that if the filtration is right continuous, if these are equal, then optional times are stopping times, full stop. Let's prove this quickly. If tau is an optional time with respect to the original filtration, then for any non-negative time, if we look at the event that tau is strictly less than a time a little bit bigger than t plus 1 over n, that event decreases to the event that tau is less than or equal to t. That is, the intersection of this countable family of events is this event here. But each of these is an event in the filtration at some time s bigger than t, which means that intersection is an element of Ft plus. So for each non-negative time, the event that tau is less than or equal to t is in Ft plus, which exactly shows that tau is an Ft plus stopping time. For the converse, if tau is an Ft plus stopping time, then for any strictly positive time, we can similarly construct the event that tau is less than t as a union over all the events that tau is less than or equal to anything less than t, in this case taking that union over natural numbers of the event that tau is less than or equal to t minus 1 over n. This union is by definition in Ft minus, which is contained in Ft. And that shows that tau is an Ft optional time. And now to conclude the proof, we just need to check what happens at 0, but of course at time 0, the event that tau is less than 0 is the empty set, which is always in F0. So that shows that tau is an Ft optional time, concluding the proof. Just to be especially pedantic, we will not make the standard assumption throughout these lectures that our filtrations are right continuous, and so I will point out when results apply to optional times versus stopping times. But in reality, most of the time you'll be working just with stopping times because you'll make the standard assumption that your filtration is right continuous. Now, in the discrete time setting, back in lectures 45, the place that stopping times really came up was hitting times for Markov chains on certain sets. So those should be our canonical examples of stopping times, or maybe optional times. Well, let's take a look. Let's fix some measurable subset of our state space S, and for a stochastic process of interest, look at the hitting time of that set. We'll denote that, as we did before, by TA. That's the infimum of all strictly positive times where xt is in the set A. Now, that could be different than what we called the passage time before, but in the continuous time setting is usually called the debut time, which is the infimum over all t greater than or equal to 0 of the event that xt is in A. In both of these definitions, we will, as usual, define the infimum of the empty set to be infinite. So, of course, these times can take infinite values if the process never reaches the set A. Now, of course, if at time 0 the process is not in A, then these two random variables will be equal. And in general, of course, since here we're taking an infimum over a smaller set, it follows that TA is generally bigger than dA. So those are true of these random times, but the question is, are these things stopping times, or maybe they're only optional times? Let's fix some event in the probability space that has probability neither 0 nor 1. We could say take a probability 1/2 event. And let's define a stochastic process like this. The process stays at 0 for a while and then starts increasing linearly at rate 1 after that. But for each outcome, the time that it starts increasing depends on whether we're in the set E or not. That is, xt stays at 0 and then starts increasing at time 1 on the set E, and xt stays at 0 and only starts increasing at time 2 in the event that E does not occur. Well, if we take the event A in the state space to be the interval from 0 up to infinity, then since this process, which always starts at 0, does not start in A, we get that the hitting time of A and the debut time of A are always equal for this process. We can write out what they are explicitly. That's equal to 1 on the event E and 2 on the event E complement. Note, at those times the process has not reached A, but since it is in A for all times strictly greater than those times, those are the infima in question. In particular, we see from this that the event that TA is less than or equal to 1 is just the event E. However, xt is equal to 0 for all t in the unit interval. And so, therefore, the natural filtration generated by this process is just the trivial filtration up to time 1. And since E was selected to be an event that has probability not equal to 0 or 1, it's not in this filtration. So that shows that the event that TA is less than or equal to 1 is not in the filtration at time 1. And so the hitting time of this set is not a stopping time. Now this is a great concrete example of a filtration here that will not be right continuous. And you can check that if you ask about the event that TA is strictly less than 1, well, of course, that's the empty set and will be in the filtration at time 1. And in fact, TA and dA will be optional times in this example. So this shows that without right continuity, hitting times and debut times may not be stopping times. But if the set is nice enough, they will at least be optional times. Let's look at a result now. On a general filtered probability space, consider an adapted process, xt, which we will assume has right continuous paths. By what we proved in the last lecture, by the way, that means that it's progressively measurable, which means that it makes sense to take the composition x at a random time tau. If that is measurable, this will produce a new measurable random variable. That's a side comment, but we will evaluate x tau at the certain times tau we're interested in here in step 2 of this proposition. Here are the results. If we start with a subset of the state space A that is open, then the debut time and the hitting time of the set A are always equal, and that time is an optional time, not necessarily a stopping time, as we saw in the last example, but always an optional time. That's about all we can say when the set is open. If the set A is closed, then if we evaluate the process X at the hitting time or at the debut time, that will produce a point in the set A. Of course, it only makes sense to do so if we make the additional conditional assumption that the debut time or the hitting time are finite, because we haven't defined what x infinity is otherwise. Now, it's important that A be closed for this, because as we'll see, what we really will prove is that this point is in the closure of A in both cases. Now, if we make the additional stronger assumption that the process not only has right continuous paths, but actually continuous paths, then we have the following nicer results for closed sets. If A is closed, then the debut time is always a stopping time for continuous path processes. Whereas if A is closed, then the hitting time is always an optional time, and it's almost a stopping time. What we'll show is that the event that the hitting time is less than or equal to t is indeed in ft for all strictly positive times t. But to be a fully fledged stopping time, we'd also need to know that the event that the hitting time is less than or equal to 0, meaning equal to 0, is in ft, and that's not necessarily true. All we can say in general is that it is in ft+. And here is an example to show why that can happen. We can have a process which, in some outcomes, has paths that look like this. In this case, the set A is the singleton point little a here. This process hits A in value at times arbitrarily close to 0. It oscillates around A and hits A infinitely often over there. And that means that in this outcome, TA is equal to 0. But that's impossible to tell from the sigma field generated by x0 alone. You can't tell that the process is going to oscillate madly in the infinitesimally soon future past time 0, knowing only what it does at time 0. So in fact, the event that TA equals 0 is generally, for processes that can look like this, not in the natural filtration of the process at time 0. But it is, of course, in the infinitesimal future sigma field f0+, which talks about what happens in an arbitrarily small but positive time interval in the future. By the way, Brownian paths, as we'll soon see, always look like this. And that's the reason why the natural Brownian filtration is not right continuous. All right, let's prove these in turn. First, for step 1, under the assumption that the set A is open, we want to see that the debut time and the hitting time of the set are equal. Well, as we already commented, those are always equal on the event that the process starts outside of A. So we just have to see what happens in the event that the process starts in A. Well, we're assuming that our process has right continuous paths. And that means that the limit as t goes down to 0 of xt is equal to x0. Now x0 in this event is in this open set A. And if I have a sequence in S that converges to a point in A when A is an open set, it then follows that a tail of that sequence is in that open set. So that says that xt is in the set A for all sufficiently small t greater than 0. But that means that both the hitting time and the debut time of A are equal to 0. And so in all cases, those two are equal when A is open. Now, still in this case where the set A is open, we want to see that that common hitting/debut time is an optional time. So we look at the event that the debut time, say, is less than t. Well, this is an infimum, and for that infimum to be strictly less than t requires that there is some time strictly less than t where the event occurs. So this shows that this is a union of these events, but it's an uncountable union, which is hard to work with. we will use the right continuity of the paths of the process to reduce that to a countable union. I claim that this is the same as the event that there exists some time s before time t that is rational, where xs is in A. And that's just because xs is the limit, as r goes down to s, of xr. Now, because A is open for that limit to be in A, that means that xr must be in A for all r sufficiently close to s. But of course, there will be rational numbers in this small but non-negligible interval. And therefore, this is equal to the event that this happens at some rational time. Therefore, this is the union over that countable family of times of the event that xs is in A. But that event, since the process is adapted, is in fs, and since all those s's are less than t, that's contained in ft. In fact, it's contained in ft minus, which is contained in ft. So this is a countable union of events in ft, and therefore is in ft. And that shows that dA is an optional time. Okay, now we turn to the case where the set A is closed. Here, still assuming only that the paths of the process are right continuous, we'd like to show that if we evaluate the process at TA or dA, we get a point in A. We'll just deal with the case of TA for now, and we'll condition on the event that that hitting time is finite. Well, by definition, the hitting time is the infimum over all positive times t, where xt is in A. And by the definition of infimum, there is a sequence of times tn, random of course, that decrease to ta such that xtn is in A. But that means by the right continuity of the paths that x at time ta is the limit as n goes to infinity of xtn, and those are all in A. So therefore this is a limit point of A, but A is closed, and that means therefore that this is in A. The argument for the debut time is similar, and so I'll leave that to you. Great. Now let's make the additional assumption that the paths are actually continuous. We'd like to show that the debut time is actually a stopping time when A is closed, and the hitting time is almost a stopping time, but at least an optional time. Well, for these, we're going to work with the event that the debut time, say, is strictly greater than t, the complement of the event that it's less than or equal to t. Our goal is to show that that is in ft, to show that dA is a stopping time. And I claim that that is equal to the event that xs is not in the event A for any time s less than or equal to t. Well, the forward containment of that is clear. It's always true, regardless of whether A is open or closed, or the paths are continuous or not, just from the definition of this infimum here. For the reverse containment, this follows by right continuity of the paths and openness of the set A complement, following exactly the same argument that we gave up here. Now, since we're assuming that we have genuinely continuous paths, what that means is that the image of the process in any particular outcome on the whole interval from 0 up to t, which I'll write like this, that's an image of a compact set under a continuous map, and it is therefore a compact subset of the state space. Well, the state space is a metric space, and so what that means is that I have a compact set here, which is disjoint from this closed set A here. And in a general metric space, it follows that those two are separated. That is, the distance between them is strictly greater than 0. And since it's strictly greater than 0, then for each outcome, there's some sufficiently large integer n so that this is bigger than 1 over n. Therefore, what we've shown is that this event, that dA is strictly greater than t, is equal to the union over all natural numbers of the event that the distance between this compact set and A is greater than 1 over n. Now this distance here, that's the infimum of the distance between any point in this image and A. And so this is the event that for every time s between 0 and t, the distance from xs to A is bigger than 1 over n. So this is a union of an intersection. And again, using the continuity of the paths, we can reduce that intersection to a countable one over rational times. This is the union over natural numbers n of the intersection over all times in the interval from 0 up to t that are rational of the event that the distance from xs to A is bigger than 1 over n. Well, distance from a point to A is a continuous function in any metric space, and therefore is a measurable function. Therefore, this function here is measurable with respect to the sigma field generated by xs. Since xs is adapted, that shows that this event here is in fs. All of those times s are less than or equal to t, so that's contained in ft. And that shows that this countable union and countable intersection of these events is in ft, which is what we needed to show to demonstrate that the debut time is indeed a stopping time. And now finally we turn to show that the hitting time is an optional time. And in fact, as I said, we're going to show that it's almost a stopping time. We'll show that for any event A in S that is closed, and again assuming that the paths of the process are continuous, the event that the hitting time is less than or equal to t is in ft, provided t is strictly greater than 0. While the event that the hitting time is less than or equal to 0 is only known to be in f0 plus. Once we've done that, by the way, this shows that the event that ta is less than t is, using the same argument now that we've given a few times, the union over all s in the rationals less than t of the event that ta is less than or equal to s. And that is by what we've shown here in fs minus, which is contained in ft. And so therefore that shows that ta is an optional time. The definition of optional time only requires us to look for t strictly greater than 0 after all. So to prove this stronger claim, we'll look at the two cases separately. First, let's look at what happens when t is greater than 0. Then the event that ta is greater than t, well, that's the event that the process up to time t inclusive never touches A, just as we considered in the last slide. And because we're talking about the hitting time here, we don't know what happens at time 0. This is s strictly greater than 0. So we can write that as the event that this happens for s greater than or equal to some delta, which is strictly positive. And then we'll do as we did before, and note that that's the same thing as the event that the distance from that set of points in the metric space to A is strictly greater than 0 for every such delta. Well, for any such outcome, if this is greater than 0, then it will be bigger than some 1 over m. And also, it's good enough to take those deltas to be of the form 1 over n. And so we can write this event that the hitting time is strictly greater than t is at least contained in, but in fact by the continuity of the paths will be equal to, the intersection over all n, although we better take that n bigger than 1 over t, of the union over all natural numbers m of the event that the distance from all of the points xs with s in the interval from 1 over n up to t to A are bigger than or equal to 1 over m. And inside here, that is an intersection over all of those points, and there are uncountably many, but again, using the continuity of the paths, we can write that simply as the intersection over all of those times that happen to be rational of the event that the distance from xs to A is bigger than or equal to 1 over m. And again, exactly as before, distance to A is a continuous map, which means that this is measurable with respect to the sigma field generated by XS. And so this event is in Fs. And that's a big countable intersection and union of events in Fs for s less than or equal to t, which is therefore in Ft. Showing that we do have this in Ft, which is just shy of showing that this hitting time is a stopping time. But what happens at time 0 is the question. Well, at time 0, the event that the hitting time is strictly greater than 0 is, by the openness of the set A complement, the event that for all times in some little interval ahead of 0, that is, for some delta greater than 0, xs is not in A for all s less than delta. And therefore, by the same arguments we made above, the event that Ta is greater than 0 is equal to the union over all natural numbers n of the intersection of all times s in the interval from 0 up to 1 over n that happen to be rational of the event that xs is in A complement. But of course, this is in Fs, and this intersection is therefore, for every n, an element of F0 plus. So this is a union of events in the sigma field F0 plus, and so is in F0 plus. But we cannot prove that it's in F0 because, as we've seen, there are examples where it's not. And that concludes the proof. So we see that there are many nuances and subtleties to stopping times and their cousins, optional times, in the continuous time setting, and we also have to be careful about examples of hitting and debut times, as we've seen, that are not always stopping times, but will be stopping or at least optional times in the case where the set that we're talking about hitting or debuting from is open or closed in our metric space, state space. In the next lecture, we will extend the ideas from lecture 45.3 about the sigma field generated by a stopping time, f tau, to the continuous time setting.